Well, thanks, guys. Again, my name's Paul Elliott, WB6CXC. I'll tell you a little bit about myself on the second slide. And again, if you're here because of what you saw in the one of the printed programs, are we okay? Oh, it's not full. Gee, that's no good. That's probably going to be okay. That should say Turn Island Systems. Okay, I'll explain. I've got a little company, very little. We're trying to lose as little money as possible. And I'm actually serious about that. But I make gear that has been optimized for what Dave's been talking about, SDRs, the Whispered Demon community, the Hamsci community. And I'll talk about some of that stuff that I do. I'm not here to be a salesman, but love to talk to you about it. So I'm going to talk about optimizing, So the program, it had another agenda, other topics. So if you came to see those, I apologize. I'll do my best to make this interesting. It was from like 2 years ago on the schedule. Okay, is that all there? Yeah, good. So again, I'm Paul, Turn Island Systems. I am Vice President of Tapper. Tapper's Tucson Amateur Packet Radio. We're no longer at Tucson, and we no longer do packet radio, so we got to probably rework that acronym, but that's what it is. I'm a retired engineer. And by the way, I don't have a degree, just in case anybody cares. But I've worked from analog, audio, power supply, RF, digital, most recently, high-speed fiber optics. I've been anything from repair technician to director of systems engineering and beyond. But as you can tell, I've been doing this a long time. I've been a ham since, I think, 75. Got my novice back then. Finally got around to getting my extra class license a few years ago. I don't talk on the radio much. I don't Morse code much. I've done it all, but lately, I just like designing stuff, so that's what I do. I live in Friday Harbor, which Washington State, which is a little island. It's closer to Vancouver Island, Canada, than it is to mainland USA, but spent most of my professional career in California. So I'm going to talk about SDR receiver performance with an emphasis on the 888, but the RX 888 that Dave mentioned, but this applies to, at least pieces of it apply to pretty much any SDR receiver, and in some cases, any old receiver you got. SDR receivers, they're sampling receivers, as Dave mentioned, and I will show. In essence, you take your antenna, you connect it to an analog to digital converter, and you sample it as fast as you can, and then you do something with the data. So if you're familiar with sampling theory, which I'm sure some of you are, and Nyquist is a name you're going to be hearing, one of my heroes. There's aliasing, there are artifacts. These are things that happen when you sample a signal, especially if you don't sample it fast enough or if you have signals that exceed the bandwidth that you're designing for. So those are some of the things that can happen with an SDR if you're not careful. And I'll talk about. Also, for what we're doing, especially with Hamsci and Whispered Demon, we are measuring frequencies that, you transmit a frequency, it gets received. Because of Doppler shift, because of the ionosphere, it goes up and it goes down. And talk with the Hamsci guys, they'll fill you in on all the details. Again, I just build stuff, so I'm not the expert there. But you need precise frequency measurement. And we will see Doppler shifts of several hertz easily, but we need to measure stuff a lot closer than that. And what we're doing is I'll get into that, but frequency stability and accuracy can be highly important, and a lot of SDRs don't really handle that well. So, like I said, RX 888 SDR, it seems to be kind of the new hot ticket, and in a lot of ways it really was a game changer. As I said, the principles apply to many other SDR receivers, but I'm going to use this as an example. And does this show up? Yeah, good. So this is kind of, you boil it all down, throw away the stuff that doesn't matter, and this is what you're left with inside an RX 888. It's got an antenna input. It's got a low-pass filter. I'll talk about that. It's not great, but it has a variable gain amplifier, which is, used for AGC. It also has a switchable attenuator, but let's pretend that's inside the VGA. It's, it's a function. It has an internal local oscillator. It's running at 130 megahertz. A lot of times we will crank that sample clock down to half that rate for reasons of power consumption or heating. Sometimes it seemed like the box was getting too hot if you ran it at full speed, so we cut that down. Also, cutting down the sample rate reduces the amount of data that gets sent to the computer and the computer has to process. Okay, it goes into an analog to digital converter. This signal out of the amplifier, it gets sampled at the clock rate. Analog to digital converter in the 888 is a 16-bit A to C, 16-bit ADC, analog to digital converter. That's good. 16 bits is good. A lot of the SDRs, they'll have 12 bits. Some of them have 8 bits. And you can do amazing things with an 8-bit analog to digital converter. But there's a dynamic range issue. We're going to talk about that. And 16 bits gives you 2 to the 16th discrete levels. You can digitize with that amount of resolution, which gives you 96 dB of dynamic range. And actually, you get a bit more than that because of things like oversampling, things of dither, which is because you got noise on the input. Well, if you're curious, come by to the Tapper booth, and I'll talk for hours about it. These are things I really love, so I won't, belabor the point now, but let's just say it's around 100 dB of range. Okay, low-pass filter is marginal. It's completely inadequate if you've cut the clock rate down to half of, 65 megahertz, that's half of 130, because that means signals that are above, because of Nyquist and sampling theory, any signal that is above half of your sampling clock rate it's what it gets called aliasing, and it folds back in, and you can't tell the difference. So you have to filter it out before it gets to your analog to digital converter. And I apologize, I promised I wouldn't get into that. But now, okay, so we had 96 dB or say 100 dB of dynamic range. Now we've got what's actually coming in on the antenna, and there is noise, atmospheric noise, there's human-generated noise, and there's a lot of human-generated noise these days. There's a noise floor. This is measured by the, International Telecommunications Union, something like that. And you probably can't see the numbers, but the bottom line there is basically the input noise of a typical transceiver, typical receiver. And these three curved lines are, the lowest one is quiet rural. That's kind of where I live, actually, in Friday Harbor. There's not a lot of static around there. What there is mostly natural. As you get closer and closer into town, as your neighbor puts on solar panels or you have LED lighting or whatever, the noise floor goes up. Lots of reasons. It used to be diathermy machines would add to the noise, but so the noise gets higher and higher. So that's kind of one of the beauties of modes like Whisper and FST4W and, most of the digital modes, they will actually, you can receive signals that are below the noise floor. Okay, they're actually not below the noise floor because what you're doing is you're reducing the bandwidth on your receiver. As you reduce the bandwidth, the noise you're getting, you get less and less noise because you're filtering out most of it. So actually, they're not breaking Whisper doesn't break the laws of physics, but it receives below the noise floor of your typical ham receiver with your 3 kilohertz filters on it. Okay, so that's what we're working with. And the top one, the residential, you should probably bump that up by a few dB, again, because of modern society and our love of efficient switching regulators. Let's see, do this. Yeah. Okay, now the receiver, it's got a noise floor, input referred noise. This is, everything, even a resistor generates noise. So the receiver and amplifiers generate more noise than that. So a receiver's got a noise floor. As long as the receiver noise floor is below the environmental noise floor, you can receive the signals, or you can receive the weak signals. You can receive stuff that's as weak as the environmental noise floor. This is just showing, okay, this shows that with the 888 and with many other receivers, the internal noise floor varies with, and here it's versus signal strength. What this is really showing is as the signal strength goes up, the RX888 software adds attenuators, it reduces amplifier gain, and as it adds the attenuators, that increases the internal noise floor of the 888. So let's just say it's a little bit complicated. And more measured noise floor and dynamic range. I have to thank Clint Turner, KA7OEI, for making these measurements, and I'll refer to his stuff over and over again. I highly recommend you check out his blog because he's got excellent stuff on there. Bottom line, the very far right comment shows the dynamic range depending on the gain setting and measurements he's done, and I calculated dynamic range from that. But it's in the 100 dB, maybe even 114, but that's the range. Now you'll recall I said we have about 100 dB of dynamic range because of the 16-bit analog to digital converter. So what's this mean in the real world? Well, here's some measurements I made from my home, Friday Harbor. This is not a calibrated receive probe antenna. This is just a off-center fed 80-meter dipole that I had outside the bedroom. And you can see, I'll talk about this, but the strongest signal is off to the left. That's from in the AM broadcast band. And over here towards the middle, 10 megahertz, you'll see WWV at 10 megahertz. And I live in a pretty quiet location. I'll kind of go over some more details there. Okay, huge differences. Even this, at my location, and I'm a long way from any powerful transmitters, that AM station, I checked it out, it's 500 watts. I think I have it here. Okay, thank you. Let's just I'll give you a number here. Yeah, 20 miles away, 500 watts. So it's not a powerhouse, clear signal station. If you were closer to one of those, we're talking about 117, 120 dB easily dynamic range. That's the difference between the atmospheric noise and those strong signals. And so, oh, by the way, the green line at the bottom, that's the noise floor of my spectrum analyzer. The radio noise floor, the receiver noise floor is probably about 20 dB better than that. But it's just, kind of gives you a reference line there. So we've already exceeded, actually in my house I'm pretty good. I haven't exceeded the dynamic range of the 888, but many of you probably will be in a situation where you're going to have a dynamic range problem. If you do, you're going to be getting clipping. A little bit of clipping isn't that bad actually, but if you get a lot of clipping, overscale on the ADC converter, that will result in horrible distortion, signals showing up where they shouldn't, broadband noise. It's not a good thing. So, okay, here I am in my sales pitch here. I developed this. These are filter preamps. And I'll show you how. And by the way, most of the stuff I have here, it's not technically open source, but I provide schematics and documentation and test results on my website. And if you want to build one of these, by all means, you're welcome to do it, and I welcome anybody who wants to ask questions about it. So here I've got a 30 megahertz low-pass filter. Remember we mentioned the 888 sampling at half rate, and its built-in filter, the 60 megahertz built-in filter, which kind of sucks a little bit. Well, sampling at 30 megahertz, that filter is totally useless. So this has got built-in an anti-aliasing low-pass filter. It cuts off above 30 megahertz pretty abruptly. I'm also testing right now, and they look pretty good. And you can see some samples at the Tapper booth, 60 megahertz version of this with more gain. This one is a moderate gain preamp. And often in a preamp, you don't need a lot of gain. You don't want a lot of gain, just enough to get you over the noise floors. Okay, is this showing up? Yeah, I guess so. Here you can see the frequency response. The top one's the anti-alias filter. Also, you'll notice at the low end, starting at about 20 megahertz and going down, the response is dropping off again. That's what's called a shelf filter. And you recall the ITU noise floor, and in the US, the presence of the AM broadcast band means we got stronger signals or more noise down at the lower frequency end of the spectrum. So rather than amplify that, rather than send all that noise, all those strong AM signals into your receiver, why don't we attenuate them at least a little bit to improve the dynamic range? So that plot on the bottom is, I've got a selectable shelf filter, either one section or two sections. You see it drops down, and then it's not like an AM broadcast band rejection filter. It doesn't kill it entirely, because actually some people are using these for low frequency receiver work, and they want to get some of the signals coming through. They just don't need them to be so damn strong. So the shelf filter kind of compensates for the atmospheric noise, and at least in the US, the AM broadcast band. And I think, yes, here is that same antenna of mine run through the filter preamp, different time of day, so instead of 10 megahertz WWV, I've got 15 megahertz WWV on the right. But you can, it's hard to see because the green overlaps the black, but I've dropped the AM broadcast band signal by 10 dB or a little bit more, and I've increased the 15 megahertz WWV signal by about 10 dB. That's a 20 dB improvement in dynamic range, effective dynamic range given these input conditions. And 20 dB is a big deal. It will really help your receiver. There are other ways to do this. This is what I'm doing, what I've made. Is a pretty good way, though, and we've been using them with receivers really all around the world, and they're pretty effective. This is the results of my 6-meter filter preamp. Again, I've got the shelf filter at the low end. Here you can see the high end. It runs out almost flat to just under, 55 megahertz or so. So it works for the 6-meter ham band. It works with the 888 if you're running it at full clock speed. And then it falls off the cliff. It's what's called an elliptic filter. I've got 4 sections. Anyway, it's a steep drop off. And I've played with the elliptic filter has got like rejection notches in it. That's how you get the sharp roll off. And I've tweaked them a little bit to give me the best possible attenuation in the FM broadcast band. With the 888, the FM broadcast band, 88 to 108 megahertz, even with the built-in, low-pass filter, those will alias back down into, I don't know, I think it's around, I forget, I'd have to do the math now. I didn't know I was going to have to do math here. Anyway, it kills those by about 80 dB relative, which really makes a difference. Again, plenty of ways to solve this problem. This is just one, but it's one I'm kind of proud of because I built it. Other dynamic range considerations. In the US, we're kind of lucky. In Europe, they got medium frequency broadcast bands, and we're working 40 meters here, and right next door there's a big powerful transmitter coming through. And I only speak English, so it doesn't help me. I don't know what they're saying, but and that's my fault, not theirs. So in Europe, particularly, there are transmitters, high power AM transmitters, all over the spectrum. Often they're very adjacent to the ham bands. So what do those poor guys do about it? It's tough to do. What I did here for the AM broadcast band, it's pretty simple because the frequencies are well separated. Filters, but it's really, really hard to make good, sharp filters. And sometimes people will notch out, a particularly bad station. They don't try to kill them all. They just find the worst one or two, and they notch those out. And you can buy filters for that. I don't make them, but other people do. Or you can design your own. It's not that tough, but everyone's kind of a custom job. A lot of receivers, traditional ham receivers, if you're tuning on 40 meters, they've got pre-select filters that are already in the circuit, and they will be attenuating frequencies, other than the 40-meter ham band, or at least, everything that's not close. So they take care of that dynamic range problem, and that's, you know, that's good for that application. If that's what you're doing, is you're receiving the 40-meter band and nothing else, that's an excellent solution. That's the way it's been done for, you know, I don't know, 100 years or so. When we got a wideband SDR, we're trying to receive everything from DC to daylight, or, you know, 100 kilohertz to 60 megahertz in the case of the 888. You probably don't want to filter out. We're trying to collect everything, so we don't want to filter out anything. You know, as the best we can do is maybe tailor the filtering a little bit, but you can't get rid of a 10 megawatt AM broadcast station at you know, 7.6 megahertz or whatever it is with a simple filter. So I don't know. I don't have a good solution other than custom notch filters for that. I tried playing with a filter that was multiple pass bands, very sharp filters. I'm not going to show it. I can make it work. It would work for some cases, definitely not for all, depending on what the stations are. But the thing is a total pain in the ass to tweak onto frequency. I would not want to sell it. If anyone wants to build one, I can give you my schematics and design, but it's a lot of work to make it right. So full range SDR receivers, it's a problem. We have to deal with it the best we can. A lot of narrower range SDRs, you know, the FunCube and a lot of other SDRs have got filter banks, and they do the same thing. And that works for, again, if you're only receiving like a 2 megahertz slice of the spectrum. But for full spectrum recording and reception, you know, this is what we're dealing with. Okay, noise floor. The ITU noise floor numbers, that shows you what's coming in through the air, generally over a long distance, fairly long distance. There are also lots of other local sources. Your own house wiring, a lot of common mode stuff that goes on. Ground loops, RF ground loops. You can have switching supplies injecting noise into your ground, which then, because there's no such thing as a perfect ground, that gets coupled into your receiver, coupled into other stuff. There are ways to deal with that, and to get an excellent receive site, you do need to deal with that. I can't help you. I don't have anything I can sell you to do that, but there is work being done with balanced probe antennas. Again, the HamSci and the Tapper groups are working with a couple hams and testing out various types of antennas and antenna systems that use balanced connections. These are probe non-resonant antennas, but it appears to work pretty well for attenuating or not letting in a lot of this locally generated common mode or just plain local noise, because noise can get coupled right onto your coax shield and then into the receiver. Ferrite choke clamps on the cable, they help, but they're not going to cure it. So, work in progress, things to know about. Okay, frequency stability, we mentioned, and accuracy. The 888 and others, the QRP Labs QDX transceiver, a beautiful little transceiver. I've played with it a lot. That's got a built-in crystal, and it works really well for a lot of modes. Whisper works well enough, you know, to make a contact. But for the ham-size stuff, for the propagation research, where we need frequency stability to measure the Doppler shift accurately, none of these internal clock oscillators are stable enough or are accurate enough, especially the QDX, because it's a transceiver, and when you transmit, the board heats up, frequency shifts. And I played with trying to stabilize that, finally gave up, and Hans at QRP Labs and I and others went over a lot of this, and finally I came up with, actually in conjunction with John Ackerman, another Tapper member, a design to, well, I did the QRP Labs, okay, clock adapters. What we're doing, sorry. What we're doing is we are making it easy to inject a reference clock it's not exactly a timestamp, but it is a reference clock frequency, generally 10 megahertz, but with the 888, I think it's 26 megahertz, maybe 27 megahertz. Every receiver wants its own clock frequency, but we can, using GPS-disciplined oscillators, the Bodnar is a particularly useful one, and it costs about $120, $130, not a bad little GPS-disciplined oscillator. We can inject a GPS-disciplined oscillator signal into the receiver, which then that gets converted into the sampling frequency for the analog to digital converter, and now we can accurately measure, with K9Q software and other tools, we can accurately measure the receive frequency. And for transmitters, now we can accurately control the transmit frequency. So we have clock adapters for the 888. You can buy them from Turn Island Systems. That's the one that John Ackerman and I designed. There we go. There's some pictures. The one on top is for the QDX. Probably anybody that ever wanted one has already got one. But if you do have a QDX and you want to stabilize it, I can help. The QDX needs 25 megahertz. If I've got a little board that if you already have a 25 megahertz clock source, you can inject that directly in. A little bit of no cuts and jumps, but you do have to unsolder a component and do a little bit of delicate soldering. I've also got a version where if you have a 5 or a 10 megahertz reference clock, on the upper board there, there's a little phase lock loop that generates a 25 meg clock from that input reference. Also, and the lower one is for the 888. Yeah, 27 megahertz input, and all that provides proper termination, because if you don't do it right, you're going to get reflections and noise and common mode noise and ground loops on your input reference clock. You can get spikes on that which will burn out the synthesizer chip, and this has happened. It hasn't happened when anybody's using one of these little adapters, but it's a little bit delicate input on the board. Anyway, so we've got these available. We also provide with them new backplates, so you don't have to drill a hole in the backplate to add the connector. It's really all we're doing is we're providing one more hole in the backplate, but it's cheap and easy to give you guys a new backplate for that. Okay, so that's a receiver, transmitter. A couple years ago, we had 2 solar eclipses, one right after the other, one across North America, and wanted to get a bunch of receivers out there, but also to receive you need transmitters. And for the science that we're doing with HamSci, you need accurate transmitters that you know what frequency they're on and you know that they're going to be stable. Those transmitters are kind of few and far between, so I raised my hand and said, I can do that, because I like doing that stuff. So I put together a 6-band simultaneous output transmitter, called it the Beacon Blaster, and we put a bunch of them out there in line with Eclipse and elsewhere. Yeah, okay, so it started out at the bottom. You can see I built the thing in a modular approach because we didn't really know what we wanted exactly, and I wasn't totally sure I knew what I was doing, so put it together with pieces, but using clock synthesizer chips and let me see, what did I say here? Using a little microcontroller in there that I kind of cloned one of the Adafruit Arduino style boards, just stole the controller design from that and put it on my own board, on the main board. It's not a little plug-in. Have a reference for 10 megahertz GPS disciplined oscillator, and I have clock generators that provide the outputs. If you can see the bottom line there, I mentioned using output divider frequency control, minus 45 dBc spurious, decibels below carrier. If you want to talk about SI 5351 clock generators, that's like the most popular clock generator chip in the world. A lot of ham gear uses it, and I love the device. And if you want to talk about spurious levels and different modulation techniques, come over to the Tapper booth and I'll talk your ear off. Okay, so this was the Beacon Blaster 6 channels. That's cool, but it was kind of a pain to build, modular, bunch of cables, bunch of boards that I had to secure. So I decided I can improve this. So 6 bands good, 8 bands is better, right? So we got 8 bands on this. I was able to improve the spurious response outputs down to generally 60 dBc or better using a different modulation technique. That meant I couldn't get as many outputs from the 5351. And again, I can fill you in on all the details if you want to hear them. But better signal, more bands. These things, well, what do I talk about here? Yeah, okay, another one. So you can come, I got this set up over at Tapper, and I've got a spectrum analyzer on it, so you can see what the outputs look like, and I can describe any little piece of it you want. We're also transmitting it, transmitting 100 microwatts. I got a bunch of attenuators on that, going to a little whip antenna. So probably ERP is a nanowatt or something, and it's transmitting through the building to a receiver antenna that we have set up and a 888. So you can see the output of my WSPRSONDE going through the Tapper, being received at Tapper. I don't think I've been received anywhere else. I checked, and so far the receiver on the bench next to me is the only one that's reported.
Oh, you must mention you have a number of these in distributor.
Yeah, actually, I will get to that. Thank you, though. Yes, there are a number of these all around, but wait, there's more. So what do? We got 8 outputs, and as I mentioned, I think, well, I'll mention it somewhere. These outputs are actually square waves. Each output channel can be run anywhere from 1 megahertz to 60 megahertz. You know, we prefer the ham bands, but it could go anywhere. They're not dedicated to any given frequency. But you can't put a square wave out into the air, you know, if you want to be a good citizen. So, or meet FCC spec regulations. So we need to filter those. And I'd rather not put up 8 individual antennas when I can get a perfectly good end-fed long wave, end-fed half wave and 80 meter, 10 meter antenna. And it'll give me pretty good match on all the bands that I'm transmitting on. So how to combine those signals into one output. These square wave signals and end up with one output that meets the specs for harmonics and spurious. The spurious is already taken care of by the transmitter design, but the harmonics, okay. And I will show you how, but first, yes, a little bit of a brag here. I've got the WSPRSONDES 8, actually a bunch of them, but the ones I'm particularly fond of, one at VE3KTB, that's as close to the North Pole as you can practically get. Got another one down, and that's up at Ellesmere Island, Canada. And then we got one down on the Antarctic shelf. This is the Neumayer German research station. They've got one of those running there. And I've got another one running right on the WWV facility, Fort Collins, Colorado, just in the same building and right next door to WWVB, which is, what is it, 100 kilowatt transmitter putting out its 60 kilohertz time reference signal. And let me tell you, I was a little bit nervous when I told we're going to be putting up my antenna and my transmitter right next to these 100 kilowatt transmitters. But yeah, I thought sparks would fly, but it's been working great, so I'm really pleased about that. Okay, this is what's inside the WSPRSONDE. I already talked about it a little bit, but there's a controller board, GPS input, reference clock input. I also have a GPS. Question? Yeah, sure.
Yeah, I just wanted to say that the other night, the one at Ellesmere Island heard the one in Antarctica.
That's great. Yeah, because there is a 888 receiver that Rob Robinette helped set up. Well, I helped him too, actually, up at Ellesmere. So there are 2 sites at Ellesmere Island. They're a couple miles away, and on a good day they can get from one to the other. And on a bad day they can't. You should see what happens to the antennas in the snowstorms up there. So they've got a transmitter and a receiver. So that's pretty cool. I'm glad to hear that. Thanks, Phil. So I've got this 4-clock generators. Again, talk to me if you want to learn how to communicate with 4-clock generators on a single I2C control bus. Got a controller which does all the kind of heavy lifting of the programming and actually the timing, because the Whisper and FST4W timing is the way we're doing it. It is incredibly accurate because we can, and why would you not make it incredibly accurate if you could? So it is. And then I have these 1-watt output amplifiers, and they're really just massive digital buffers. There we go. This is a prototype. Notice I'm using those 4 integrated circuits in the middle there. Those are just octal bus drivers. I think they're octal. And I'm setting them up in a kind of a push-pull arrangement and feeding a transformer, a 2-to-1 step-up transformer. And I'm driving them with a 3-volt digital signal. The actual amplifier board itself is powered on 5 volts. So you get 10 volts peak-to-peak at the input of the transformer, and it's a 2-to-1 step-up transformer. So unloaded, it's 20 volts peak-to-peak square wave. It's a pretty good square wave, not perfect. I also have the ability, not on this board, but on the WSPRSONDE itself, to shut down 1/2 of the push-pull stage. So it cuts the voltage swing by 1/2, which cuts the power to 1/4. So instead of 1 watt, it's 250 milliwatts. So that's an option. You can have it high power, relatively high power, or low power. Here's the schematic. There will be a quiz, so I will expect everyone to have memorized it by now. Here's the output, square wave output. You'll notice a true square wave doesn't have any even harmonics. It's only odd harmonics. We got your odd harmonics right here, but we also have even harmonics because it's not a perfectly symmetrical square wave. So, got to filter that out. How do we do it? This is a 9-band filter combiner. I've done this with surface mount parts, but here there's so many bands, they're so close together, really couldn't get the performance out of this low Q, high loss surface mount inductors. So I'm using toroid cores, which makes this a highly labor intensive board because each one of those cores has got to be tweaked. These are actually coupled. You can see at the bottom. Yeah, they're at the bottom. You can see it. Anyway, each one of those needs to be adjusted. So 80, 40, 30, 20, 17, 15, 12, 10, and 6 meters. Yes? Running out of time. Come on, what, 1 minute? Yeah. 1 minute, okay. It filters it really well. We can get 8 bands on one antenna. Come on by and I'll show you how it works. Hey, I'm getting to the end. GFSK. Well, Whisper and FST4W, which is, FST4W is almost Whisper, but it uses a slightly different modulation technique. You can see on the left, FSK, hard frequency shifts. GFSK, more gradual. Yeah, you can see this. I'm doing this digitally, sampled step response to give myself a GF. Every one of those steps, I change the frequency a little bit. And there you can see the sidebands. The tall, noisy one is Whisper with a hard FSK. The bottom one is FST4W. And you can see this, what you might call spurious sidebands are way down. Probably nobody cares but me, but I think it's pretty cool. And got resources. Please come by and ask me more. And thank you very much.
Please come by the Tapper booth if you found any of this interesting. We are happy to talk.
Or even if you didn't, we'll make it interesting.